Hi, my name is Nicholas Dwork, and today we're going to discuss the MRI Signal Equation. Let's first talk about magnets. Magnets have a north and a south pole, and then they have field lines that travel from the North Pole to the South Pole. Slightly separate topic, which turns out to be exactly the same topic, are electric currents. Electric currents traveling through a wire generate a magnetic field. So here we have a wire in the vertical direction. The electric current is traveling down, and this makes magnetic field lines that are circles according to the right-hand rule around the wire. You can take a wire and make loops with it, and then this is a visualization of the magnetic field that is generated when electric current goes through that wire. And what you might notice is that it looks very similar to a magnet. Indeed, it is a magnet. This is what you call an electromagnet. It's an electric current through a wire that's generating a magnetic field such that the resulting object acts like a magnet. Now let's talk about the Bohr model of the atom. Every atom has protons, neutrons, and then electrons that orbit around the nucleus consisting of the protons and the neutrons. Hydrogen is the simplest atom. It consists of exactly one proton with an electron that's orbiting around it. Now this orbiting electron is indeed an electric current. It's a moving electron in space. The electron orbits the nucleus. This is a current. Current induces a magnetic field, and the atom becomes a tiny magnet, the tiniest electromagnet. Here we have a bunch of hydrogen atoms, and so they're each little tiny electromagnets, and they all have a magnetic vector. Here the vector is pointing from the electromagnet's south pole to its north pole. And so in general, because these little electromagnets fight against each other, the vectors are randomly distributed, and the net magnetic vector is 0. If we take this same clump of atoms, though, when the particle is placed in a large external magnetic field, its vectors preferentially align with that magnetic field. This generates a non-zero magnetic vector. That is, each of our little electromagnets preferentially align with the external magnetic field, and then they all build up slightly in one direction. And this is the magnet that we're going to see with MRI. As you imagine, the more of these atoms you have in a location, the larger this vector will be. We define a coordinate system centered on this particle. And then we come to Bloch's equation. Bloch's equation governs the behavior of a magnetic particle in the presence of an external magnetic field. Here, gamma is the gyromagnetic ratio, and for hydrogen, it's 43 megahertz per Tesla. Mostly, Bloch's equation is a cross product, and we'll ignore T1 and T2 for now. Perhaps we'll discuss that in a later lecture. So Bloch's equation dictates a left-handed precession if the external magnetic field be not or in the z direction, and if the net magnetic vector of our bunch of particles was in the x-hat direction, then we would see the net magnetic vector precess around the external magnetic vector. And the frequency of precession is called the Lamour frequency. Okay, so this net magnetic vector m is rotating in the xy plane of the lab frame. Just like current or changing electric fields changes the magnetic field, similarly, changing the magnetic field generates a current in a nearby wire. And so this spinning magnetic vector induces a voltage in nearby MRI coils, and that voltage is what the MRI system measures. Let's consider a separate coordinate system that's rotating at the Lamour frequency, and in this separate coordinate system, the net magnetic vector of our bunch of particles doesn't move. It's stationary. So it's like we eliminated the external magnetic field. We'll only consider the rotating frame from now on. It's convenient to represent the xy component of the net magnetic vector m as a complex number mxy. So here mxy is equal to mx plus I my. The B0 field is constantly on in an MRI machine. It's generated by currents passing through cryogen-cooled superconducting coils that are under the plastic sheath. The patient is lie down on the bed, and then the bed moves into the bore. The patient enters the bore, and the magnetic state of static tissues reaches an equilibrium. And this is the alignment with the external magnetic field. We then pass current through field-altering coils to alter the total magnetic field. And so here's what happened. The patient's in the bore. There's a coordinate system that's centered on the patient. And then we pass current through gradient coils to change the z component of the magnetic field as a function of space. The capital G here represents the strength of the gradient magnetic field. This is the change to the external magnetic field in the laboratory frame as a function of space. bz prime is equal to x prime times gx prime plus y prime times gy prime plus z prime times gz prime. So for example, if gx prime and gy prime are all 0 and gz prime is greater than 0 for some small amount of time, here's our z prime axis. This goes through the patient. We have 3 different particles located at different z prime locations. We turn on the gradient coils for a little while, then we turn them off. And what has happened is we've encoded the location of each of these particles into the angle of the net magnetic vector, either the angle or its phase. Precessing magnetization in the xy plane induces a voltage in the receiver coil. The signal that we get out is proportional to the voltage that results from the sum of the precessing magnetization of all of the particles. So it's this sum of their magnitudes and phases. Phase is just the integration of frequency, and frequency is the gyromagnetic ratio times the magnetic field strength. In this case, it's proportional to the gradient times the location. Assuming the particles don't move and taking the limit as the particle size goes to 0, we arrive at this equation. This equation is very special, but we're going to make it look a lot nicer. Let's do this simple variable substitution where we replace the integral with this k value, and we end up with this expression. This is the Fourier transform. This is a well-known expression, and it's especially nice because it's invertible. That's how we're going to recover our image. We recover mxy with an inverse. This is the spin warp trajectory. Here I'm showing the excitation pulse, which is outside the scope of this presentation. The gradient is 3 different components: gx prime, gy prime, gz prime, and the time that we'll acquire data. So we start by exciting. This places our probe in the k space at the 0 frequency. We then move the probe by turning on gx prime and gy prime for a little while. And then we turn on gx prime and collect data as we do so. We repeat this process for many different lines, and this is our Fourier data. This is the data that we're going to use to reconstruct an image. Here's what the Fourier data looks like. It always has this star-shaped pattern with the bright spot in the middle, and it sort of degrades as it goes out. We simply apply an inverse discrete Fourier transform, and out comes our image, in this case a sagittal slice of the knee. This is from the MRIdata.org dataset. Thank you for your attention.